Good. Good morning, everyone. This is Joseph Hominy from Orton Ceramic Foundation. This is the first time we're teaching this course online, and it's a joint effort between the American Ceramic Society and Orton. Also online, helping me out getting everything right is Greg Geiger from the American Ceramic Society. So today's lecture, we'll do an introduction to refractories, and we'll go over the first series of properties on thermal properties. If you have any questions, you can interrupt me at any time. You can email me after the lecture. I'll get back to you. And this will be recorded, so you can view it up to 30 days after the course is over. And at the end of the course, we'll have the Dropbox. You can download all the slides. There's probably about 1,400 slides right now. So I'd like to get started, and we'll start with the introduction, and we'll define what a refractory is. Refractories are materials that are used at high temperatures, but their performance is also affected by other environmental conditions, and these are mechanical stresses. So they have to be load-bearing structures. They're also affected by thermal stresses. They're subjected to thermal cycling, which gives rise to thermal shock. And they're also subjected to thermal gradients. They're also subjected to erosion and corrosion by gases and molten materials, and the molten materials would be molten metals, slags, and glasses. Now, when you look at the materials that are available to manufacture refractories, you're looking at materials that are low cost and high volume. So there's a very limited amount of elements that fit this criteria. For the cations, the positively charged ions, you have silicon, aluminum, magnesium, calcium, chromium, and zirconium. So there are 6 elements that are the cations that are most commonly used. And for the anions, the negatively charged ions, you have carbon, oxygen, and nitrogen. So these 9 elements pretty much make up all the refractories that are in production today. So these elements can be combined to form oxides, non-oxides, or they can be used in elemental form. The oxides are SiO2 silica, Al2O3 alumina, MgO magnesium, CaO calcia, and some of these have some unusual problems associated with their use. Calcium oxide is unstable in water, so it hydrates. Cr2O3 chromia is volatile at high temperatures, and ZrO2 zirconia exhibits phase transformations. We'll go over all of these issues when we talk about each type of refractory material. The non-oxides that are commonly used are silicon carbide, silicon nitride. Silicon carbide is SiC, silicon nitride is Si3N4, and in elemental form, carbon is used. So these different oxides and carbides can be combined to form other compounds, or they can be combined to form composites. So that gives rise to a great number of other materials. And when you classify a refractory, you can do it based on physical form. That's a shaped refractory, an unshaped refractory, or a refractory in fiber form. Or you can do it on chemical composition by oxides, non-oxides, or composites. The oxides are classified whether they're acidic, neutral, or basic. An acidic oxide might be SiO2 for an RO2 group. A neutral oxide might be Al2O3 for the R2O3 group, and a basic oxide might be MgO for the RO group. So I like to classify refractories based on their shape and their chemistry. So a shaped refractory would be a fired refractory brick, an unfired cast shape, a fusion cast refractory, or an insulating refractory. And then we can go through the oxides, the non-oxides, and the composites. The first oxide is silica, SiO2, and we'll devote a lecture to each one of these oxides in the next couple of days. Silica exhibits three different crystalline forms: cristobalite, tridymite, and quartz. And when you classify a silica refractory, it's a conventional refractory. It has 0.5 to 1 weight% impurities. If it's a super duty refractory, it has 0.2 to 0.5 weight% impurities. So a super duty is a little bit more pure than a conventional silica refractory. So silica is crystalline in one of these three forms: cristobalite, tridymite, and quartz. There's also another version of silica which is amorphous called fused silica, which has a certain unique properties relative to the crystalline silica, such as low thermal expansion. The next group of oxides is the alumina silica materials, and we'll start out with fire clay. Fire clay has two crystalline forms, mullite and cristobalite, and they're ranked based on their use temperature from low duty to medium duty to semi-silica to high duty to super duty. So going from low duty to super duty, you're increasing the use temperature from about 1430 degrees C to about 1763 degrees C. And we'll go over the PCE test later on, but the PCE is the pyrometric cone equivalent. The higher the number, the higher the deformation point. So a low duty is a PC of 15, and a super duty is a PC of 34. The other group of alumina silica refractories are the high alumina materials, and they start at 50% alumina, and they go up to 60, 70, 80, 90, and 99 weight% alumina. So you can see the PCE values go up from 34 to 40, and the use temperatures go from 1763 to 1885 degrees C. The high alumina materials have corundum and mullite as the major crystalline phases. The basic oxides are magnesia, lime, and dolomite. Magnesia is MgO or periclase. Lime is CaO or calcia. And dolomite is a combination of MgO and CaO, a combination of periclase and calcia. Other basic oxides are magnesia chromia or chromia magnesia or chromite. So magnesia chromia has the majority of the phase present as MgO, followed by Cr2O3, and there's also some Al2O3 present. So the crystalline phases are periclase, chromia, and spinel. If it's chromia magnesia, the majority phase would be Cr2O3, followed by MgO and Al2O3. So that's chromia, periclase, and spinel are the same crystalline phases present, but there would be more chromia in a chromia magnesia spinel and more periclase in a magnesia chromia material. The other basic material is chromite, which is Cr2O3. There's an FeO impurity, which forms a spinel crystalline phase. A few more basic oxides are forsterite, 2-MgO-SiO2, it's a magnesium silicate, and spinel, which is MgO-Al2O3. If it's stoichiometric, it's 1-to-1 MgO to Al2O3, and it's all in the spinel phase. If it's MgO-rich, it's periclase and spinel. If it's alumina-rich, it's corundum and spinel. Other oxides are based on zirconia, ZrO2. First one is zircon. It's a zirconia silicate, ZrO2, SiO2. That's zircon, is the crystalline phase. And then there's zirconia, and I mentioned that zirconia has a phase transformation issue, so you have to stabilize it. And this one is stabilized with lime CaO. So this is a lime stabilized zirconia. And then a common refractory is AZS, alumina zirconia silica, which is Al2O3, ZrO2, SiO2. Corundum, badiolite, and glass are the phases present. I listed glass, it's amorphous. That's a major component in this refractory. The non-oxides are carbon, silicon carbide, silicon nitride, and mixtures of silicon carbide and silicon nitride. Carbon can be completely crystallized in the graphite form, or it can be completely amorphous in the carbon form, or it could be any combination in between amorphous and completely graphitized. So it could be partially graphitized and partially amorphous. Silicon carbide, the high temperature form is alpha silicon carbide. Silicon nitride, the high temperature form is beta silicon nitride. And then of course you can have the composites where either one of these components can be the matrix and other component, the particulate. So it's a silicon carbide, silicon nitride material. The other group of materials are composites, and there are a lot of different combinations here. The first one here is that I picked is silicon carbide carbon. So SiC, probably dispersed in a carbon matrix. And so you have alpha silicon carbide and graphite. Alumina carbon, common for ladle linings, Al2O3 carbon. So you'll have corundum and graphite present. Magnesia carbon, which is common lining for a basic oxygen furnace. You'll have MgO dispersed in a carbon matrix, so you'll have periclase and graphite. And this is a more complex one, maybe for a tube, maybe in a tun dish. Alumina, silica, silicon carbide, and graphite. So you'll have Al2O3, SiO2 will probably be there as the amorphous form of silica, fused silica, silicon carbide, and your carbon bonding phase. So mullite, cristobalite, alpha silicon carbide, and graphite. Those are all shaped refractories. The unshaped refractories are unfired. They're in the form of a castable, a plastic, a gunning mix, or a mortar. The castables can be, the binding phase in the castable can be a hydraulic cement or a chemical binder. The plastic will have a chemical binder. The gunning mixes will have either a hydraulic cement or a chemical binder. They can be gunned cold to form a lining, or they can be gunned hot to do a repair. The mortars are either heat setting, air setting, or hydraulic setting. The other form of refractories are the fiber form, the ceramic fibers. And these are the typical compositions. The lower grade would be 40 to 60 weight% alumina. You're going to have mullite and cristobalite as the crystalline phases. The higher alumina content, to 95 weight% alumina, will be corundum and mullite for the crystalline phases. And then ZrO2, which would be a stabilized zirconia. The other one on the previous slide was stabilized with CaO. You can also stabilize it with Y2O3 yttria. The fiber materials can be in the form of a blanket, a board, or they can be loose fibers. So a flexible blanket, a rigid board, or loose fibers. So that's how we can classify all the different types of refractories. And it turns out that refractories are a hidden industry, but they're the enablers of productivity. So almost everything that is in modern society somehow depends directly or indirectly on some type of high temperature process. So if you look at metals, they're processed with refractories. So are ceramics, glass, and cement, electronic materials, the petrochemical industry, chemical process at high temperatures. Heat is generated, and so is electricity. If you look at the consumption by industry, steel industry is the major consumer of refractories, so oil is at least 55%. The major furnaces in the steel industry are the blast furnace, the basic oxygen furnace, the BOF, the electric arc furnace, EAC, and the argon oxygen decarburization vessel, AOD. The blast furnace makes iron, the basic oxygen furnace makes steel, and the AOD makes stainless steel. The non-ferrous metals, some examples are production of alumina and of aluminum and remelting of aluminum. And the ceramics industry, tunnel and shuttle kilns are used. In the glass industry, you have the melting tanks. Minerals processing, some examples are a rotary cement kiln or a vertical lime kiln. Chemicals would be petroleum reaction vessels, and there's utilities and others. So iron and steel is about 55%, non-ferrous metals about 10%, ceramics about 10%, glass melting about 5%, minerals processing about 5%, chemicals about 5%, utilities maybe 1%, and there's other applications like incineration and so on. So that's about 9%. So that's a quick introduction on the different type of refractory materials that are available and how they're classified. Are there any questions on that? Okay. So when we talk about properties, we really want to talk about structure-property relationships. So we want to consider the properties of refractories in terms of their structure, because the structure controls the property. So there are different structural levels that we can look at. We can look at the electronic level, which are the valence of the ions or their electrons. We can look at the atomic size, valence or bonding. We can look at the crystal structures, which are the unit cells. And we can look at the microstructure. And I've underlined microstructure because it's the most important part most important structure that we want to consider for refractories. These are structural elements you can observe under a microscope. The macrostructure are structural elements on the size scale of the object. So when you characterize the microstructure, you determine the quantity, size, distribution, shape, and chemical composition of all the crystalline and glassy phases. And you have to include porosity because that's a major part of a refractory material. So for structure-property relationships, we want to relate the basic properties to the microstructure of refractories. And we'll keep in mind that refractories are very heterogeneous materials. So we have to account for the heterogeneous nature of refractories. So refractories are typically a coarse and a medium-sized grain, and grain is a polycrystalline material in some type of matrix. So the bonding matrices are ceramic bonding, which could be a silicate glassy phase, direct bonded, where you have a solid state reaction that bonds the crystals together without a glassy phase. You can have carbon bonding, where you have a carbon precursor, such as a resin that pyrolyzes at high temperatures to form carbon. You can have hydraulic bonding, which is a calcium aluminate cement, a high temperature cement, or a colloidal dispersion of, let's say, alumina, which also provides hydraulic bonding. Or you can have chemical bonding, maybe a phosphate or a silicate bond. So most refractories are a coarse or medium-sized grain, polycrystalline grain, and a bonding matrix of some type. So with that background on how the structural levels affect the properties, we want to spend the rest of today on thermal properties, which are volume stability. And volume stability has two sections: reversible changes, which are thermal expansion or thermal contraction, or irreversible or permanent changes. We also want to look at heat capacity and then thermal conductivity. So for volume stability, the definition of thermal expansion, which is a reversible change, A is the coefficient of thermal expansion. That equals delta L, which is just the change in the length, divided by the original length, divided by the change in temperature, delta T. So L is the length, T is the temperature. So it's simply the change in length divided by the original length and the change in temperature. The units are inches per inch degrees F, centimeters per centimeters degrees C. The length units cancel. So basically A is just 1 over F or 1 over C. You can also have a volume expansion instead of a linear expansion. So alpha is the volume expansion coefficient. That just equals the change in the volume divided by the volume divided by the change in the temperature. So V is the volume, and now the units are cubic inches per cubic inch degrees F or cubic centimeters per cubic centimeters degrees C. Just rewriting this equation for thermal expansion into a much simpler form. A equals the final length L sub F minus the initial length L sub 0 divided by L sub 0, the initial length, and that's divided by the difference of the final temperature minus the initial temperature. So T sub F minus T sub 0. And again, this has the same units. So why do materials like refractories expand? What's the origin of thermal expansion? On the atomistic level, thermal expansion just corresponds to an interatomic separation distance as you increase the temperature. So atoms in these materials are vibrating in these asymmetrical potential wells. So the potential energy is the sum of an attractive force and a repulsive force. So the potential energy E equals this first term here, minus A over R to the N. This is the Coulombic attraction term. A is a constant, R is the interatomic distance, and N is another constant, plus the second term, which is the overlap repulsion term. B is a constant, that's divided by R to the M. Again, R is the interatomic distance and M is another constant. N is usually 1, M ranges from 3 to 10. So if you plot that equation and you're plotting potential energy versus interatomic separation, this dotted line is the repulsive term, and this dotted line, which continues through here, is the attractive term, and the sum is this asymmetric potential energy well, and that's where the atoms are vibrating in that potential energy well. This position here at the bottom of the well is the equilibrium position at 0 degrees K, where there's virtually no vibration. And then as you see the way this potential well is asymmetric, it just tells you there's a lower force required to separate the atoms than to bring them together. So if we look at increasing the temperature from absolute 0 to T1 to T2 to T3, where T3 is greater than T2 is greater than T1, these horizontal arrows represent the vibrations in the interatomic separation. So you can see as we increase the temperature, the amplitude of the vibration increases. And if you look at these horizontal midpoint lines on each temperature, you can see that they're shifting to the right as you go up in temperature. So these vertical lines represent the new interatomic separation at each one of these temperatures. So as we go up in temperature, the midpoints move to the right, so we have thermal expansion. If this potential energy well was completely symmetric, these points would not move and there's no thermal expansion. But materials like that don't exist. They all have this asymmetric potential energy well. So that's the source or origin of thermal expansion. You basically increase the temperature, you increase the energy level, you increase the amplitude of vibration, and that increases the average interatomic separation distance. So if we take an oxide, which is an ionic material, and compare other materials to oxides, if we look at covalent materials, which are stronger materials than oxides, that would be the carbides and the silicon carbide and silicon nitride. They have stronger attractive forces. They have lower thermal expansion. The potential energy well is more symmetrical than for the oxides. Metallic materials, they have weaker attractive forces, so they have higher thermal expansion and a more asymmetric potential energy well. So some typical values of thermal expansion for ceramic materials. These are some different oxides. The first three are typical refractory materials: alumina, Al2O3, magnesia, MgO, and zirconia, ZrO2, and two other oxides, thorium oxide and uranium oxide. You can see they're all around 10, 12, 13, and that's centimeters per centimeter degree C times 10 to the minus 6. And these are average coefficients of thermal expansion from 0 to 1,000 degrees C. MgO happens to be the highest, 13.5 times 10 to the minus 6. So it has the highest thermal expansion of the refractory materials. This slide shows some other materials. It shows the carbides: silicon carbide, titanium carbide, and boron carbide. You can see they're lower. This is 4.7, 7.4, and 4.5, and that's all times 10 to the minus 6. So these have lower thermal expansion coefficients compared to the oxides. And I put glass here. This is just window glass, sodium lime silicate. Glass is a major component of a lot of refractories in the matrix. And that's about 9 times 10 to the minus 6. So it's in the same range as the oxides. And I also listed fused silica, fused SiO2. It has a very low thermal expansion coefficient. That's 0.5 times 10 to the minus 6. When you're looking at an application for a thermal shock resistant material, a low thermal expansion is a very desirable property because it limits the thermal stresses that can develop. This slide shows expansion versus temperature for some typical refractory materials. The highest one here I mentioned is MgO, magnesia. The lowest one here, I mentioned that silicon carbide was low. It's on the low end. And here are three different aluminas, a 60 to 70%, an 80 to 90, and a 99%. So as you increase the alumina content, you increase the thermal expansion. Phosphorite was that magnesium silicate. And then this one is a little bit different. It's silica. Silica goes through a phase transformation where there's a crystal structure change and a change in volume. So there's a rapid increase in its thermal expansion at a low temperature, and then it tends to level off, becomes pretty flat, it becomes a constant. And that's because the crystal structure of silica is unique. It has some open volumes in the crystal structure, which allows vibrations to take place that actually pull the structure together instead of pushing it apart. I have a second slide here on thermal expansion of some typical refractories. This is the linear expansion versus temperature again. And I put on chrome, which is highest on this graph. The lower one might be zircon, has a fairly low expansion coefficient. And in the middle here, I have a silica fire clay and a regular fire clay. And then again, I have the silica on this diagram, two Super Duty silicas where they go through the phase transformation and then tend to level off on the thermal expansion behavior. And then this slide is pretty busy, but it has a lot of the refractory materials on the same slide. So again, thermal expansion versus temperature. At the top of the graph are the basic refractories. These are the numbers 2, 3, 4, 5, 7, and 8. They're right up here. They have the highest thermal expansion. And as you decrease the MgO content, you decrease the thermal expansion of these different compounds. And the middle of the diagram are the alumina-silica refractories. They'd be 9, 10, 11, 13, 14, and 15 in this range here. Again, as you decrease the alumina content in this direction, you decrease the thermal expansion coefficient. So the basic refractories are the highest thermal expansion. The next lowest are the alumina-silica. Now close to the bottom are the non-oxide refractories, 16 and 17. And these are silicon carbide and silicon nitride bonded silicon carbide. And all the way in the bottom are some low expansion materials. The number 18 is cordierite. It's a magnesium aluminosilicate. 19 is fused silica. And 20 is spodumene, a lithium aluminosilicate. So these materials at the bottom have low thermal expansion behavior, but unfortunately, they're low temperature materials and not really useful for refractories, but they are low thermal expansion. And fused silica may be the one that has the highest use potential, maybe 1300 degrees C. And unfortunately, after you reach that temperature, it starts to crystallize and go back to the crystalline form of silica, perhaps tridymite or cristobalite. So I mentioned that MgO had the highest coefficient of thermal expansion among the refractory oxides, 13.5 times 10 to the minus 6. It has a compact cubic rock salt structure. So atomically, it's a very dense packed material. It's highly symmetric, and it doesn't have any internal spaces to accommodate lattice vibrations. So therefore has a high thermal expansion coefficient. So this is the cubic rock salt structure. The dark circles would be MgO, and the open circles would be oxygen. And over here, the black circles are MgO, and the lighter colored circles are oxygen. So it's a very dense structure that exhibits high thermal expansion. And I mentioned that fused silica has the lowest coefficient of expansion among these different refractory materials, 0.5 times 10 to the minus 6. The structure of amorphous silica is based on SiO4 tetrahedra. The structure lacks symmetry. It's a random glass structure. It's basically tangled arrays of SiO4 tetrahedra. This structure has a lot of open internal space to accommodate lattice vibrations. So that's why it has a low thermal expansion coefficient. So here are two silica tetrahedra. The smaller circle in the middle of the 4 oxygens would be the Si, and this would be the oxygen. And there's a bond angle that's variable, theta. So for a glass, theta might vary from 120 to 180 degrees. So this arrangement, the way they're bonded at the corners, allows for a low thermal expansion coefficient. So for the structural aspects, we can consider single crystals. So in a single crystal, the thermal expansion depends on the crystallographic direction. And these are the different crystal structures: cubic, tetragonal, hexagonal, triclinic, orthorhombic, or monoclinic. In a cubic structure, you have only one expansion coefficient because it's isotropic. So no matter what direction you are in that crystal, you have the same thermal expansion coefficient. In tetragonal and hexagonal crystal structures, you're going to have 2 expansion coefficients because it's anisotropic. And in triclinic, orthorhombic, and monoclinic, you have 3 expansion coefficients. It's also anisotropic. So we'll talk about crystal structures a little more when we talk about the chemistry of each type of refractory. But this is a diagram of the different crystal structures I just mentioned. There's cubic, which has a body centered or a ion or cation in the center. And the cubic also can be face centered with atoms on the faces. There's tetragonal and tetragonal body centered. Orthorhombic with 2 faces centered, body centered, or all faces centered. Monoclinic face centered, triclinic, and 2 versions of the hexagonal crystal structures. So if we look at a common refractory material like graphite, it's hexagonal. So this is what graphite structure looks like. These small dark dots are carbons. So the axis here, perpendicular to these basal planes, the C-axis is perpendicular. Both A-axes are in the planes of these different layers. So there's a 6-member carbon ring that forms these hexagonal layer structures. If you're looking at the thermal expansion in the A direction, it's 1 × 10⁻⁶. There's very strong covalent bonding in these layers, so very low thermal expansion. But if you're looking in the C direction, parallel to the C-axis, it's 28.3 × 10⁻⁶. So it's about 28 times higher in this direction than in this direction. And these are average coefficients from room temperature to 1,000 degrees C. So if it's not a cubic crystal, you're going to have this anisotropic behavior in the thermal expansion coefficients. And here's some examples. Alumina Al2O3, aluminum titanate, mullite 3Al2O3 2SiO2 is a very common refractory material. TiO2, zircon, another common refractory material, ZrSiO4, and then a calcium carbonate, CaCO3. So they're hexagonal structures. This is A perpendicular to the C-axis and A parallel to the C-axis. You can see that these have lower expansion coefficients than these on the right. Alumina is not too different, 8.3 and 9.0. Aluminum titanate is minus 2.6 and 11.5. Again, there's a negative thermal expansion coefficient here because it has an open structure that allows it to accommodate vibrations in that direction. Mullite is 4.5 and 5.7. TiO2 is 6.8.3. Zircon is 3.7 and 6.2. And then the calcium carbonate also has a negative thermal expansion in one direction and a large thermal expansion in the opposite direction. These are all room temperature values. So what's important about this? The most important thing to remember, if you have an isotropic versus an anisotropic thermal expansion behavior in a polycrystalline material, the isotropic materials do not develop microstresses when they're heated or cooled, but the anisotropic materials develop microstresses during the heating and cooling cycles. When that happens, it builds up stresses and it forms microcracks. So microcracks are formed to provide stress relief. The stored strain energy in the material is converted to fracture surface energy of the crack surfaces. So most refractory materials are going to be severely microcracked. And this is an example of how this works. This is an anisotropic polycrystal, TiO2. If you form a powder compact of TiO2 and you heat it up to the sintering temperature, you form a dense material. And then as you cool it down, you have a certain thermal expansion behavior, and then microcracks develop on cooling. So these microcracks are opening up as the material is contracting, so it gives an apparent thermal expansion that is now lower than this because the slope is lower than this slope. And then when you heat it up, the microcracks close as the material is expanding, and it again gives a lower thermal expansion coefficient than this region here where the microcracks are closed. So at the sintering temperature, you have a dense coherent structure. When you cool it, microcracks develop. The TiO2 material contracts while the microcracks open. You have this lower apparent coefficient of thermal expansion. When you reheat the material, the microcracks close. TiO2 is expanding. The microcracks are closing. You now have a lower apparent coefficient of thermal expansion. And you end up with the hysteresis effect, opening and closing of microcracks as you continue to cool this material. So this table contains like crystalline materials, and it's the ratio of their perpendicular thermal expansion coefficients. Anytime this ratio is greater than 1:1, you're going to have microcrack. So if we just look at a few of these, Al2O3 is hexagonal. The ratio is 1.09 to 1. Cr2O3 is also hexagonal. It's 1.3 to 1. Fused silica, vitreous silica is 1:1. So there will be no cracking in that material. So a lot of the refractory materials are not cubic, so they're all going to exhibit microcracking because of the different expansion coefficients in the different crystallographic directions. Refractories are not single crystal materials, they're polycrystalline, different compounds. And here's an example of Al2O3, Al6, Si2O13. And this is the ratio of the expansion coefficients at the phase boundaries. So two different crystal materials coming together have different thermal expansion coefficients. Anytime that ratio is greater than 0, you're going to have a potential for microcracking. So you can see on this first one, alumina and mullite, it's 1.67. So it has a great potential to form microcracks. Here's another one, ZrO2, zirconia, and ZrSiO4, 1.16. So if you look at all of these, they're all greater than 0. So refractories are composed of multiple phases. The potential for microcracking is over there. The other thing we can look at is composites, two dissimilar materials. Again, if the difference at the boundaries are greater than 0, you're going to have microcracking. So this first one is an MgO carbon composite. MgO would be the matrix, carbon would be the inclusion. There's a thermal expansion mismatch. MgO has a larger coefficient. It puts carbon in compression, and the mismatch is 2.86. So you can see that all of these are either C for compression for tension, and they're all greater than 0. So any of these composite systems could cause microcracking. This is an MgO reinforced with a metal iron fiber. That's why it's Fe. So what we should take from this is that almost all heterogeneous refractory materials are going to be susceptible to microcracking. That degrades the microstructure because of the thermal expansion anisotropy. So this starts at the manufacturing of the brick shapes, and it takes place at the first cooling cycle after firing. As you continue to thermal cycle the material in an application, it forms more and more microcracks. So what do the microcracks do? Well, on the mechanical properties, microcracks are flaws. And when we talk about mechanical properties, We'll see how flaws lower the strength of materials. So microcracking decreases this. But sometimes you want microcracks in a refractory material. Like if you want a material with high thermal shock resistance, you want microcracks present because they continue to grow and dissipate the stored elastic strain energy from the stress field. New surfaces, you have a stable situation where you have stable fractures instead of a large decrease in strength when you're measuring the strength relative to a thermal shock resistance. So refractories generally have microcracks present. They decrease the strength. They decrease other mechanical properties also, like the elastic modulus, but they also enhance some properties like thermal shock resistance. So they're desirable in some cases and undesirable in other cases. And I put this one slide on because glass is a major component of a lot of the refractories, especially the aluminum silicates. So this is the thermal expansion versus temperature for a typical glass. And the first part of this curve from room temperature to the glass transformation temperature, you have normal thermal expansion behavior. Above the glass transformation temperature, the material actually starts to become less viscous and allows a change. They're increasing the thermal expansion behavior, a steeper slope. At some point, it becomes less viscous and more fluid. That's the softening temperature. And then it starts to shrink because it softens. So glass is one of the phases present in a lot of refractory materials. So this just summarizes that previous slide. Below the glass transformation for the glass, you have normal linear thermal expansion. Between the transformation temperature and the softening temperature, you have normal linear thermal expansion, plus you have a configurational change giving rise to a more rapid thermal expansion change. And then above the softening temperature, the material just deforms because it becomes very fluid. So where do you use thermal expansion data? You use it in furnace design. There's usually a metal shell in a furnace that is a constraint. So you have to know the thermal expansion of the material to allow thermal expansion joints or gaps in the structure. On the microstructural level, crystal expansion mismatches and anisotropy and phase transformations. You want to be aware of these types of issues to design a microstructure. And on the macrostructural level, you have thermal gradients, you have external constraints, materials are subject to thermal shock. So thermal expansion knowledge helps you design for all of these situations. Now, I put in all of these lectures how to measure the different properties. So they're all ASTM tests. And this first one, ASTM E228, is how to measure thermal expansion with a normal pushrod dilatometer, which is the most common way you measure thermal expansion or thermal contraction. So we measure linear thermal expansion of solid materials. If we're looking at 180 with liquid nitrogen temperatures to about 1,000 degrees C, you can use a fused silica pushrod tube dilatometer system. Fused silica has the advantage that it's very low thermal expansion, but above 1,000, 1,200 degrees C, it starts to crystallize and change. So you can use a fused silica pushrod dilatometer in this temperature. If you want to go to higher temperatures, you go to an alumina pushrod tube system, which you can go to about 1,600 degrees C, which is useful for most refractory materials. If you have to go to very high temperatures, you have to go to graphite pushrod and tube. You can go to 2,500 degrees C, and you have to do that in an inert atmosphere to protect the graphite from oxidation. Most of the pushrod dilatometers, you can measure thermal expansion greater than 0.5 times 10 to the minus 6. So that's the lower limit, or that's 0.5 parts per million. So this is the range where you have fused silica. So how you summarize this technique, you have a single pushrod and tube. You measure the change in length of a sample relative to that of the sample holder as you're heating up the material. You heat it or cool it at a constant rate, and you have to calibrate with a known reference material. So what it measures is the mean coefficient of linear thermal expansion, alpha M. So that's the final length of the sample minus the initial length divided by the initial length. And then again, the temperature difference, the final temperature minus the initial temperature. So that's just our definition, delta L over L0 divided by delta T. But it's the mean coefficient of linear thermal expansion because it's averaged over the temperature range between the final and initial temperatures. The significance of the thermal expansion measurement, we mentioned you can use design purposes. You need to determine dimensional changes of structures that are subject to temperature changes to allow for thermal expansion mismatches. And you can determine thermal stresses that can occur as a result of temperature changes. Some important points on a pushrod dilatometer. The materials that you construct the dilatometer have to be stable. So whether it's a fused silica or aluminum or carbon, that material has to be stable over repeated heating and cooling cycles. The sample holder and pushrod have to be made of the same material. And you're running usually a small sample, 1 or 2 inches in length. So they must be homogeneous and representative. And that sometimes poses a problem for refracting materials. Most of the aggregates are 1/4 inch, sometimes they're as large as 1 inch. So there are other machines that I'll talk about a little bit later where you can put a much bigger sample in case you have a really coarse microstructure. But this works fairly well for most refractory materials. The holder and pushrod beyond the sample has to have identical thermal gradients. So the holder and pushrod are heated slow enough to prevent radial thermal gradients. The pushrod is inside the tube. So you have to heat it slow enough so they both heat at the same rate. So I mentioned this typical sample, 1 to 2 inches, that's about 25 to 50 millimeters. The cross section is about 5 to 10 millimeters, maybe a 1/2 inch in cross section. And this is what a sample might look like. This end would be the holder, this would be the pushrod. And you want to make sure you have a stable situation where the sample doesn't move during the actual heating and cooling cycles. So this has a curved pushrod in contact with the flat end of a sample. This pushrod and holder have curved ends, and so does the sample to have more of a point contact. This is a typical refractory sample. This one is 2 inches long and approximately a 1/2 inch in cross section. It looks like a castable, aluminum silica castable material. This is a schematic diagram showing a little more detail of the sample holder and pushrod. This one is for a fused silica system. So this is you can see the tube. There's 2 types of tubes here. One has a closed end, one has an open end. And then this is the sample sitting between the end of the tube and the pushrod. So when the sample expands, it moves the pushrod and you have a sensor at the other end of the push rod that measures the displacement. And I mentioned that what you're measuring is the difference between the sample. If it's a 2-inch long sample, you're measuring the difference between the 2-inch long sample and the 2-inch long sample holder. So when you have a fused silica push rod holder system that has a very low thermal expansion and you put a high expansion refractory in like MgO, you're measuring a big difference between the sample and the sample holder, and you'll get a for the thermal expansion. When this material has a low thermal expansion, the sample has a low thermal expansion like fused silica, the difference between the sample and the sample holder is almost zero, and that's where you have your limitations on measuring thermal expansion. Here's the actual sample holder from one of our dilatometers. This is a fused. You can see the sample holder, and then here's the push rod inside the sample holder. There's a thermocouple coming in an alumina tube. And then this is the sample. It looks to be about a 2-inch long sample of fused silica. It looks opaque because it's a ground surface. So that would be a calibration sample. So your sample holder, your push rod, your sample, and your thermocouple. And this is another example with an alumina push rod and holder system. Here's the push rod. Here's the holder. This is a platinum calibration standard sitting in there. And you have your thermocouple. Ideally, you want to put the thermocouple as close as you can to the sample to get an accurate measure of the sample temperature. So this is a schematic of the entire system. Push rod dilatometer system. You can have a furnace for heating the sample. I mentioned that you can go down to liquid nitrogen temperatures. So you'd have a cryostat for cooling. So you can do a heating cycle or a cooling below room temperature cycle. You have a transducer that measures the length change, a very accurate transducer, plus or minus 1.3 microns. So this part would be the sample holder. You have a sample sitting in the sample holder. You have your thermocouple measuring the sample temperature. Your furnace, these are the heating elements surrounding the sample. The push rod goes outside the furnace to the transducer sensor. And I mentioned that you want the probe rod and the sample holder, which actually continues longer distance than shown here, to be heated uniformly so that they expand the same. So you minimize error between the expansion of the probe and the sample holder outside the sample. So you try to measure the difference between the sample and the sample holder. All of these machines have to be calibrated. You have to have a machine output from a known calibration standard. The list of the standards: stainless steel, aluminum, fused silica, and platinum. So different samples for different calibration ranges. We mostly use platinum for the ceramic refractory type materials. If we have a really low expansion material, we'll use the fused silica. And just for your reference, I put down some different tables of temperature versus expansion for different calibration standards. These are standards that used to be available. Some still are available from NIST. You can purchase them. So here's a borosilicate glass, expansion versus temperature, a stainless steel, and a fused silica. Here's platinum versus temperature, aluminum versus temperature, and two other materials, Lucalox, which is a transparent alumina, and then transparent because it's very fine grain size, and then thermographite, which is just graphite. So those are the different types of calibration standards. And you take one of those standards and you put it in the dilatometer and you heat it as a function of temperature. So you measure your reference material. So B is the correction factor. So delta L over L0, and this is sub T, that's for the true expansion of a reference material. That's what I just gave you in the previous tables. So you know the expansion coefficient or the expansion behavior of your reference material, you measure it, and then you either subtract or add what the machine gives you. So delta L over L0 of the measured expansion of the reference material or the machine expansion. So at every temperature, as you heat it and cool, let's say you're going from room temperature, maybe 20 degrees C to 1,000 degrees C, at each temperature point, you would take the standard thermal expansion and you'd add or subtract the correction to that for your correction factor. So the correction factor takes place at each temperature during heating or cooling. So you measure the initial length of the sample and you have an initial temperature T0. You heat for the heating cycle at usually at 3 degrees C a minute. And that's a slow enough heating rate to uniformly heat the push rod and sample holder without developing thermal gradients. So then you have delta L over L0, which is what you measure at the transducer when you have your sample in. Actually, that's the corrected. This is what you measure at the transducer, delta L divided by L0 sub A, which is the measured thermal expansion. We have our correction factor B. You add those two together, you get the thermal expansion of the material, delta L over L0. So delta L over L0 just equals this term, delta L over L0, that's measured by the transducer, plus the thermal expansion of the standard minus the correction factor. So that's how the dilatometer works. And you end up with a mean coefficient of thermal expansion. And I just mentioned maybe from room temperature, 20 degrees C to 1,000 degrees C. So that would be your delta T. And the length at, let's say L2 would be at 1,000 minus L1 at 20 divided by the initial length, the temperature T2 at 1,000 minus T1 at 20. So you get your average coefficient of expansion over that temperature range. And when you plot that, this is percent linear change versus temperature. This material is a fairly high thermal expansion, but you can see you have almost linear behavior. It's not quite linear. No materials are exactly linear, but some are pretty close. And we also, in our reports, generate a table. So this table is a partial table. The slide I just showed you is room temperature to 1,000 degrees C. This one is room temperature to 600. I just didn't show it all. But you typically record the temperature, and this one's printed out every 20 degrees, but you're actually recording at every degree C. The time it takes to reach those temperatures, the percent linear change, and then your average coefficient of thermal expansion, this number times 10 to the minus 6, and that's per degree C. So this is a fairly high thermal expansion material. It's probably not a refractory, it's probably a metal of some type. So this is their mean coefficient of thermal expansion. And I didn't mention it, but you can also calculate a differential coefficient of thermal expansion, which is the instantaneous thermal expansion at any temperature. So it's just the slope at a particular temperature. What people use are the mean coefficient of thermal expansion, alpha CTE, because that gives them a thermal expansion over an entire temperature range. This is just the instantaneous. It's useful to see if there's a phase transformation taking place, an abrupt change in the thermal expansion behavior, but it's not useful really for design purposes. The other type of volume stability we want to consider is irreversible changes. So far, we just talked about reversible changes. So on a reheat change, we can define it as a measured length of the sample. You then go to a desired temperature with a desired hold time, and you measure the length again. So a reheat change looks like a thermal expansion coefficient, but it's the final length minus the initial length over the initial length times 100 to get percent. So the units are percent. So you heat a sample, you measure it prior to heating, you hold it at some time, it's usually 5 hours for an ASTM standard, you bring it back down to room temperature, and you see if it's the same length as you started out with. It's either going to be larger or smaller or the same. So why is there a reheat change? Well, the microstructure is not at a steady state equilibrium for the new environment that you put it in. So maybe you fire a refractory at 1,000 degrees C and you use it at 1,200 degrees C. It's a different temperature. Maybe the atmosphere is different, but it's going to be a situation where it re-equilibrates to the new environmental conditions. So reheating at existing environmental conditions produces a permanent increase or decrease in size. May not do it depending on the system, but in most cases, you'll have a change in length that's permanent. So once you equilibrate at a new steady state equilibrium after reheating, you now go back to completely reversible thermal expansion once you stabilize that material under the new conditions. Reheating continues a high temperature process. So what are these processes? You can have a chemical reaction. You can form a new compound that has a different density and therefore changes the volume. You can have crystal phase transformations. You can have decomposition reactions and gases coming off. You can nucleate and grow a new phase. Or you can have the sintering process where you have a densification or shrinkage, and that occurs by illumination and porosity. So different processes that give you this irreversible shrinkage, sintering and densification, and there are a series of sintering processes. You can have a solid state sintering, you can have viscous flow sintering, and so on. That densifies the material and shrinks it. You can have a liquid phase formation. One of the phases may melt and cause densification. You can form a glass. You can anneal a glass and change the density of the glass. You can recrystallize the glass and change the density. You can relieve residual stresses, change the volume. Something can volatilize, or you can have grain growth. So all of those give rise to shrinkages. You can also have irreversible expansions. Microcracking opens up the material. Thermal shock creates microcracks, which can open up the material. A phase transformation can make the material appear larger. Thermal expansion mismatches create microcracks. A phase change, a chemical reaction, bloating from a decomposition of a material that gives off a gas phase. You can oxidize a material like silicon carbide or silicon nitride, or you can have a decomposition reaction. So there are a lot of processes that give rise to shrinkage and expansion that's permanent. And this table shows some typical refractory materials and typical ranges of their permanent linear changes. So if we look at one here, a basic refractory, high MgO refractory brick, reheated to 1700 degrees C. It's a high temperature refractory. It might shrink maybe 1%, or it might expand 0.5% depending on the chemistry. If we look at a 60% aluminum brick, reheated to 1600 degrees C, it might shrink slightly, maybe 0.2%, or it might expand up to 4.5%. And when we go over the compositions of these different materials, I'll explain why these changes take place. This is a 60% aluminum monolithic material reheated in the range of 1650 or 1600 C. And depending on the chemistry, you might have a shrinkage, maybe 0.7, or an expansion of 3%. And then these materials here, BC is a bloating clay that expands. C is a cast material, G is a gun material, P is a plastic, R is a ram material. So typical values, there may be a shrinkage of 1% or so, and an expansion of maybe 6% or so. And I have some plots here of some different materials, and these are castable refractories. This one is a 90% alumina castable. The dotted line, the finely dotted line is a low cement fire clay castable, and the solid line is another fire clay castable. So when you start out here at 0 and you heat them up, the first thing you might see is a slight dip, a slight shrinkage at 500-600 degrees F, and that's because the cement dehydrates. Over here, you start going through expansion, and then at higher temperatures, two things start happening. You start having some shrinkage, but at the same time in materials, you may have mullite formation. Mullite's a lower density material, so it's going to have a volume expansion. Here you're forming mullite, and now you have two competing processes. You're starting to sinter at the same time, so it starts to shrink. So all of these exhibit maybe a little mullite formation and some sintering and shrinkage going on at the same time. So when you cool it down, you see that they're somewhat below 0. This is about a permanent change of 1%, and these are about 0.5%. So there's a permanent linear change. And now when you heat and cool these things, if you held it at these temperatures long enough, you'll probably get linear heating and cooling on these materials. These are some plastic refractories. There's a 70% a mullite plastic, a Super Duty fire clay plastic, and a high alumina plastic. These have a lot less shrinkage. They're going through heating, and you'll see some shrinkage here on some of these. It looks kind of flat because you may have mullite expanding it, forming at the same time you're having a sintering process. So they're exhibiting this type of behavior. But when they're cooled down, there's a permanent permanent reheat change. And I have another plastic that's quite different than those other three. Again, expansion versus temperature. We start out with expands. You start up, it levels off because there's two competing processes, sintering and mullite formation. Sintering shrinks it, mullite expands it. Then the mullite formation takes over, and then you stop it and you cool it back down. And you see there's a permanent positive change here of about 0.5%. So depending on the chemistry, these things may have a permanent shrinkage or a permanent expansion. And I just put in a few of these other materials, the magneslate. So this is MgO in basically a graphite or carbon matrix. And these have different metal additives for improving the oxidation resistance. This one has aluminum, this has silicon and aluminum, and this one has aluminum and magnesium. We'll go over in great detail how these composites are made later. But one of the first things that you see here is a dip, and that's when the resin pyrolyzes to form carbon. So there's a little bit of a shrinkage. And then these things are usually pretty stable. You might see little changes where metals might be oxidizing, and these metals are there in 1%, 0.5%, 2%. So they're not there in great volume. So where do you use reheat data? Well, you have to use it again in structural furnace design. just like you use thermal expansion. It determines the maximum use temperature, especially if there's a negative change. When the material starts to shrink, you don't want to use it past where the shrinkage starts because you're going to open up cracks in the lining. Or you can use it to control dimensional changes. You can tailor changes in these refractories at the use temperature. Maybe you want a zero change. Maybe you want the refractories to expand and have a positive residual change. A lot of times in steel ladles, you want to line with bricks and not use a mortar. So you design a material that has a little bit of a positive change that closes the joints and makes it tight to metal penetration. So reheat data is useful for furnace design to allow for expansion joints and useful for controlling dimensional changes to tailor a material for an application. And we'll go over this in the last day on microstructure design of refractories. The ASTM test, I think this is the last thing we have before break, that measures reheat change of a refractory brick. So you're just measuring the permanent linear change. And the standard designates prescribed heating conditions. So there's appropriate heating conditions for each type of refractory material based on their use temperature. So refractory brick of different compositions exhibit unique permanent linear changes after heating. Again, we mentioned they're due to chemical reactions, decomposition reactions, nucleation and growth, sintering shrinkage, and they're useful in research and development, developing products. And these are given in specifications from refractory producers because the consumer needs to know what the reheat change is. The normal sample size for a reheat is what's called a 9-inch straight brick. It's 4.5 inches wide by 2.5 inches thick, or sometimes it's 3 inches thick and 9 inches in length. This is a typical sample of a high alumina refractory brick. It's 9 inches long, 4.5 inches across, and this is probably 2.5 inches thick. These are high temperature markers. You have to measure the before and after length changes at the same location. So it looks like they measure 2 lengths in the long 9-inch direction and a width perhaps on the top and bottom of the sample, and also the thickness in the same place. The equipment, you need a furnace capable of going to at least 90 degrees F, so you need a high temperature furnace. They're usually gas fired. You have to follow a certain heating schedule, and you want to have an oxidizing atmosphere. So to run the test, you measure the length of the sample before reheating. You have to put the sample on its 9 by 2.5 or 3-inch face, the smallest face in the length direction, and you place it on a material of the same composition. And you could put a refractory powder between the 2 pieces, or you could just leave them without the powder. But when you put a reheat sample on top of a material of the same composition, they should both shrink uniformly. You don't want to put a reheat material on something that expands at a different rate or contracts at a different rate because it might affect the length measurement on that side of the sample. It might restrict or constrain the expansion, or might cause it to expand more. So for each material, you select the appropriate heating schedule for that type of refractory, and you do the reheatings, and then you measure the sample length after. So these are a table of different reheating schedules. They go A through H. Obviously, the higher temperature would be like a high alumina material. The lower temperature might be a medium or super duty fire clay. So you can see that these temperatures go up pretty fast in short times. You get to 2190 in about 3 hours, and then you hold it for 5 hours according to the standard. So usually you use a gas-fired furnace because they can heat much faster than an electric fired furnace. The percent linear change is simply the final length minus the initial divided by the initial times 100 to give you the permanent linear change. And this is a typical report, and looks like this refractory was actually an unfired castable. So there's actually 3 measurements here: green as cast after drying, probably about 230 degrees F, and then fired at 2000 degrees F. So you get 2 permanent reheat changes here, from green to dried and green to fired. So you can see the green to dried is a small shrinkage, maybe 0.02%. And then the fired is a little higher, 0.25, and that's linear, and that's volume. And then you can see there's a bulk density change. And because it's a castable, you're driving off chemically and physically held water, so it's going to become less dense, even though it's shrinking a little bit. Okay, that takes us to about 12:30. After the break, we'll do heat capacity. It's a shorter section, and then spend the rest of the time on thermal conductivity. At this point, are there any questions? Great. So we'll take a break and come back. Well, it's 1 o'clock, so I'd like to get started on the last 2 properties under thermal properties, the heat capacity and thermal conductivity. So for heat capacity, we can define heat capacity as the increase in heat content of a material per degree of temperature rise. So the heat capacity, C sub P, just equals the change in the heat content, dQ, divided by the change in temperature, dT. And we're going to consider measurements at constant pressure, P. So the heat capacity is just the increase in heat content of material as we increase the temperature. Common units, calories per mole degree C. And for reference, a calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree C. So what are the modes of heat or energy incorporation into materials? Well, on the atomistic level, heat is stored in the vibrational energy of atoms as they vibrate around their lattice positions. But these vibrations are not independent. Each atom's not vibrating independently around its lattice position. They are propagated in terms of vibrational waves. So these lattice waves are known as phonons, and that's the major mechanism of energy incorporation for the heat capacity. It's also the major mechanism for thermal conductivity for heat transfer. The other mode of incorporation is at the electronic level. So heat is stored in the vibrational energy of free electrons. For non-metallic materials like ours, that's a very minor mechanism. So the structural aspects of heat capacity is not structure sensitive. So it doesn't depend on the crystal structure. Heat capacity does increase at a phase transition. And we mentioned phase transition in silica earlier. So when a phase transition takes place, one crystal structure transforms into another. At the time of transformation, there's a lot of random motion, so that allows for more atomic vibration. So there's a spike in heat capacity at a phase transition. It turns out the heat capacity follows an empirical law above room temperature. So the heat capacity, Cp, just equals 3 times R. R is the gas constant. So this empirical law says that the heat capacity equals 6 calories per mole degree C above room temperature. If you have more than one atom, you have to account for that. So the heat capacity would equal 3nR, where N is the total number of atoms in the formula. So if we're looking at SiO2, there's 3 atoms per formula. So it would be, N would be 3. So that empirical law holds rather well. There's many derivations that are we're not going to go over in this course that actually derive heat capacity versus temperature. So if just looking at it a little differently, instead of calories, we'll look at it in terms of joules. 1 calorie equals 4.184 joules. So in this case, CP equals 3R, 25 joules per mole. And if you have more than one atom in a formula, it's 3NR. Again, N is the total number of atoms in the formula. So you'll see heat capacity sometimes in calories, and you'll see it sometimes in joules. So in calories, it's 6 calories per mole, or in joules, it's about 25 joules per mole. So here's a plot of heat capacity versus temperature for some typical refractory materials. Room temperature is about right here, about 25 degrees C. And these are normalized. So these are divided by that factor N. So MgO would be divided by 2, silicon carbide by 2, alumina by 5, and mullite by a higher number. So they all appear to be the same because they're normalized. But you can see where 3R is, and this is in calories per mole degree C. And you can see that they all approach 3R above room temperature. We're not really concerned below room temperature because we're talking about high temperature materials, but for reference, the heat capacity drops off to 0 at absolute 0, and below room temperature is proportional to T cubed. So less than room temperature, it drops off as a cube of temperature. Above room temperature, it approaches a constant. So heat capacity versus temperature. This shows how it's not structure sensitive. Here's the heat capacity for CaO. Here's the heat capacity for SiO2. SiO2 has a alpha to beta quartz transition right here. So there's a little spike in the heat capacity. And if you physically combine CaO and SiO2, you get a curve that looks like the upper one here. You still see the phase transition. Or if you chemically combine them to form a calcium silicate, you'll get a curve that looks like this without the phase transition. So it's basically additive. You're adding CaO and SiO2, and you're getting either chemically or physically, they're the same answer. So it's not structure sensitive. For glasses, heat capacity below the glass transition is the same as for crystals. But above the glass transition, where there's structural motion, it can be up to 3 times the 3R value. So you have greater molecular motion when the material becomes less viscous. So this would be heat capacity for temperature for a glass. This is a sodium borate glass. You have your typical thermal expansion behavior. You go through the glass transition, and then you have a higher heat capacity. So I have a couple slides here of heat capacity for refractories, and these are in joules per mole. So heat capacity versus temperature. So if N is 2 in our formula, our empirical formulas, the heat capacity would be about 50. So CaO, MgO, FeO, you can see roughly heat capacity is around 50. If N equals 3, an example would be ZrO2 or SiO2. It's roughly 75. That's joules per mole degrees K. And you can see the alpha to beta quartz transition taking place right here. And then for materials like alumina or chromia, where N equals 5, they're roughly 125. And then for some other refractory materials, like this is the calcium titanate, where N equals 5, it's roughly 125 for the heat capacity. For N equals 7, that might be one of these different spinel structures. Here's your magnesium aluminate spinel. It's roughly 175. And then for more complicated materials like mullite, where N is 21, the heat capacity is 525. So there's a different scale on this side. So it's about 125 there. So it's an empirical law that holds fairly well. And these are some other materials, nitrides and carbides. For N equals 1, for graphite, it's around 25. For N equals 2, for like boron nitride or silicon carbide, it's about 50. And then for N equals 1, N equals 5, the heat capacity is about 125. That would be boron carbide. So a rough empirical law that works fairly well above room temperature. Where do you use heat capacity? Well, you need it in thermal mass calculations. You can calculate the energy required to heat a furnace lining in a batch operation. You can calculate the energy required to heat whatever's in the furnace load. And you can use it for thermal conductivity calculations. We'll talk about thermal conductivity next, but the thermal conductivity is K, and that equals something known as the thermal diffusivity times the density times the heat capacity. The diffusivity is a measure of how fast heat diffuses through the material. So if you know the diffusivity and the heat capacity and density, you can calculate a thermal conductivity. And that's exactly what we do when we do a laser flash diffusivity measurement. We measure the diffusivity and the heat capacity, and you know the density, so you can calculate the conductivity. So a differential scanning calorimeter is used to measure heat capacity. So a test material is heated at a controlled rate in a controlled atmosphere over a temperature range where we want to determine the heat capacity. And we measure the heat flow into the test material relative to a reference material and a blank. So it's a continuous measurement, and the heat flow is measured relative to a reference sample. The significance of a DSC measurement, well, it's a very rapid and simple way for measuring heat capacity. Heat capacities are useful for designing purposes, quality control, and research and development. Some issues here you need to be aware of. Small specimens, we're using milligram quantities, so you have to have a homogeneous and representative sample. So for a heterogeneous refractory, you have to grind it to a fine powder and get a homogeneous sample. These specimens have to be stable over the temperature you're measuring the heat capacity. You don't want a chemical reaction. You don't want a mass loss. You can't change the mass if something volatilizes. If you have a chemical reaction, that's an endothermic or an exothermic reaction, you're not going to be able to measure the heat capacity. You can't have a sample that reacts with the sample holders. They're usually platinum. So that's another endothermic or exothermic reaction that will invalidate the test. The samples can be solid. They're usually small cylinders. They can be machined to fit a crucible to maximize the contact between the sample and the crucible, or they can be a powder, which is what we usually use for refractory materials because they're not homogeneous. Here's an example of a sample. This on the left is a platinum crucible. The top to the crucible is on the right, and in the middle is a cylinder. This is a homogeneous material. It's about 0.2 inches in diameter and a ½ inch tall, so it's a small sample. So for the equipment, the DSC test chamber, well, there's a furnace that gives you a uniform heating rate. There's a temperature sensor that measures the temperature of the sample. And then there's a differential sensor that detects heat flow between the sample and the reference. And this is usually done in some kind of environmental chamber under an inert atmosphere. You have to have a temperature controller to control the rate of temperature change, and it's usually a pretty quick measurement, 10 to 20 degrees C per minute. Recording device to record the heat flow. The specimen holders and lids, which I just showed you, have to be inert to the specimen in reference. And for the most part, we're using platinum. If we have a material like a carbide or a carbon that reacts with platinum, we'll use an alumina sample holder and lid so it won't react with it. And you have to weigh the sample accurately, so you need an analytical balance. So this is a schematic of the sample holder. It's a temperature controlled block. There's a spot for the sample, another spot for the reference. And the sample holder temperature increases in a linear function with time. And this is what the sample would look like inside its heating element. So both the test sample and inert reference sample are maintained at nearly the same temperature. And you're recording the energy difference required to keep both the test sample and the reference sample at the same temperature. So you have basically a small furnace inside the sample holder here that is maintaining the temperature of the sample at the same temperature as the reference, as you're heating the whole thing up at a constant temperature. So the first step is to run a blank. So you put the empty specimen holder and lid in the position, the sample position. So position empty sample holder lid and empty reference holder and lid in the DSC. You purge it with an inert gas. You hold it at a constant temperature to equilibrate the system. Then you heat it to the final temperature. You hold it at the final temperature to equilibrate it again, and you record the baseline thermal curve. So you're measuring heat flow versus temperature. This first curve up here is the baseline curve. That's without a sample. You next place the standard reference. In this case, we're using sapphire in the same sample holder and lid. You have to weigh the standard, the specimen holder and lid, position the sapphire standard and specimen holder and lid in the empty reference holder, position, purge it with an inert gas. Again, you hold it isothermally at a low temperature, run it up to the final test temperature, hold it isothermally at the final test temperature, and record this thermal curve. And that would be the second curve here, the sapphire standard curve. So this is a measure of the heat that's used to heat the sapphire standard. And then you make another run with the unknown sample. You place the unknown specimen in the same specimen holder, weigh it with the holder and lid, position the unknown specimen and specimen holder and lid and empty reference holder and lid in the DSC, purge it with inert gas, hold it isothermally at the low test temperature, bring it up to the final temperature, and then hold it at the final temperature to establish an equilibrium. And then you record that thermal curve, and that's the one here with the dotted line. So you have your baseline with no sample or standard, your thermal curve with the standard, and then your thermal curve with the unknown sample. So at each temperature, you have to measure these two distances, DST and DS. So this one, DST, is a vertical displacement between the blank and the sapphire standard, and DS is the vertical displacement between the blank and the unknown sample. So I'm just defining this again. DST is the vertical displacement between the blank and sapphire standard thermal curves at a particular temperature. and the units are milliwatts. And ds is the vertical displacement between the blank and the unknown sample thermal curves at a given temperature, again in milliwatts, and T is the temperature. So you do that at each temperature and get that difference. And you calculate the heat capacity as a function of temperature. So Cp is a specific heat capacity of the unknown sample. That's CPS. CPST is a specific heat capacity of a sapphire standard. And we're using specific heat capacities, joules per gram. Most of the examples I showed you were like joules per mole. So this is a specific heat capacity, joules per gram. And then you have to have WS and WST. WS is the mass of the unknown sample in milligrams. WST is the mass of the sapphire standard in milligrams. So you use this calculation at each temperature to calculate the heat capacity. For reference, I put down the sapphire standard alpha alumina, Al2O3, and that's just the heat capacity. And this is degrees C, degrees K, and then the heat capacity joules per gram, the specific heat capacity. So when you do that calculation at each temperature, you get a report that looks something like this. This is actually for a carbon refractory. And I guess these were the test temperatures. There's 6 different temperatures we took for the answer, 47 to like 271 degrees C. We calculated the heat capacity at each one of those points. And then in this report, they actually do a curve fit to get an equation for the heat capacity from room temperature to 260 degrees C. So it looks like 3 carbons were tested here. And if you plot heat capacity versus temperature, the dotted lines are the curve fits. And then these are the curve fit equations to describe those 3 curves. So that's the heat capacity for 3 carbon materials. So that's a quick run through on heat capacity and how it's measured. The easiest way to measure it is with the DSC. Does anyone have any questions on heat capacity? By the way, if you have any questions you think of later, you can always email me or call me anytime. I'm here for anytime you want to give me a call. So the last section we want to talk about and spend some time on is thermal conductivity. And there's a basic. Hello?
One question.
Yes.
The values of C sub P,
Yes.
are they a mean value between the temperature and the room temperature? Or are they
they're
measured?
at the exact temperature.
Thank you.
They're not a mean like the thermal expansion. So the basic heat conduction equation, Q, is the heat flux, and that's per unit area and time, equals the thermal conductivity K, and that's what we're interested in measuring, times the thermal gradient. So the TdX is the temperature gradient, T is temperature, X is distance. So if you're measuring conductivity or actually you're measuring heat flow through a furnace wall, you have a thermal gradient, the TdX. You have a hot and a cold phase temperature, certain thickness. You know the conductivity K, you can calculate the heat flow Q. The units for conductivity are a little strange. Calories per second, centimeter degree C, or watts per centimeter degree C. For the origin of thermal conductivity, there's 2 types of thermal conductivity. We talked briefly about phonons. Phonons are lattice vibrations. And then there's also photon conductivity, which is radiation. So we'll go over phonon conductivity first. So there's an equation that describes this. So the conductivity K equals 1/3 the summation, and omega is the frequency of vibration of the lattice waves. So if the lattice, the atoms in the lattice are coupled to form a wave when they vibrate, but they all don't vibrate at the same frequency. There's a whole range of frequencies. So omega covers that range of frequencies of the lattice vibrations. C omega is the contribution to heat capacity at each mode of vibration. Nu is the velocity, the speed of sound in the material. And L omega is the mean free path, which is a function of the frequency of vibration. So the heat capacity is the summation over all these lattice vibrations. The thermal conductivity is the summation of all of these lattice vibrations of the heat capacity times the mean free path, which are frequency dependent, times the velocity of sound in the material. The phonon conductivity is important at all temperatures, low, intermediate, high temperatures. It's how the materials conduct heat. So if you look at that equation, the heat capacity is pretty much constant from room temperature and up. We just discovered that. The velocity of sound is a constant. So the real variable is the mean free path. So the mean free path is what's controlling the phonon conductivity or the thermal conductivity. So in phonon scattering processes, you can have two types. You can have phonon-phonon interactions where two lattice vibration interact and limit the mean free path. Or you can have the lattice or lattice defects that are limiting the mean free path. So at low temperatures and intermediate temperatures, the most important process are the phonon interactions. And in that temperature range, K decreases according to 1 over the temperature. So as the temperature increases, K decreases in that 1/T relationship. The lattice spacing, lattice defects that occur at high temperatures where the phonon scattering takes place. The lattice spacing and defects are uniform in a crystal lattice. So now K becomes constant at high temperatures. So most dense refractories, they start the thermal conductivity at room temperature, they decrease as 1/2, and then they tend to level off at high temperatures and become constant. The structural aspects of phonon conductivity, well, for the crystal structure, any crystal structure that becomes complex, as the complexity increases, it lowers the mean free path and therefore lowers the conductivity. So MgO is one of the highest conductivity refractories. It's a simple cubic structure, but as you go to alumina, to phosphorite, the spinel and then the phosphorite, the structure becomes more complex. You have a lower mean free path and a lower conductivity. Just as thermal expansion was a function of direction in a crystal structure, so is thermal conductivity. So K is a function of direction in anisotropic materials. It turns out K is the greatest or highest in the direction of the lowest thermal expansion, which is the direction of the strongest bonding. And it's also the direction of the greatest velocity. So here's an example of quartz SiO2 conductivity in these units, calories per second, centimeter degree C, measured at these 5 different temperatures, K perpendicular to the C-axis and K parallel to the C-axis. It's a hexagonal material. You can see that the ratio is much different than 1. So depending on the direction in that crystal, it has different thermal conductivity. Another thing that affects the conductivity is atomic weight differences. So two atoms that have a greater difference in atomic weight, they're going to give a lower mean free path and a lower conductivity. A high conductivity material, even higher than MgO, is BeO, beryllium oxide. And if you go across from left to right, you end up here with thorium oxide, uranium oxide, heavy elements. So from left to right, the conductivity decreases as the mean free path decreases. Beryllium oxide is an excellent high temperature material, but it's very toxic, so you can't use it. But it would make a high thermal conductivity refractory, but it's very toxic. Other things that affect the mean free path are impurities. Impurities create atomic weight differences. There's bonding differences. There's strain fields that are created. All of these give rise to a lower mean free path and a lower conductivity. The grain boundaries and the grain size have no effect on the mean free path, because the grain size is not important, because the crystals are large compared to the mean free path of a typical phonon, which is about 100 angstroms. And at high temperatures, it's on the order of the lattice spacing, a few angstroms. So the grain size is much bigger than the mean free path. So the grain size has no effect. It does not scatter phonons. Glass, on the other hand, is a distorted structure. It's amorphous. It's not like a polycrystalline material with a definite crystal structure. So it has a lower thermal conductivity compared to a similar crystalline material. So fused silica would have a much lower conductivity than crystalline silica. That's a little bit about phonon conductivity. The other conductivity is photon conductivity. So that would be K radiation, subscript RAD for radiation. And there's a formula that describes the conductivity due to radiation. So it's 16 times this constant, which is a Stefan-Boltzmann constant. And that's just the constant that describes the radiation as a function of temperature for a black body. N squared, N is the refractive index, which is just a measure of how fast light travels through the material. T is the temperature. L, radiation, is the mean free path of the radiation, and that's divided by 3. Photon conductivity is important at high temperatures. You can see the term here, T cubed. So it really goes up as the temperature goes up. It's not important at low temperatures. It's very important at high temperatures. So the photon conductivity, just like the photon conductivity, just like phonon conductivity, is controlled by the mean free path, L radiation. Refractory materials are opaque. You can't see through them. So the mean free path for the radiation is 0. So there's no contribution to K radiation. However, if the material is transparent, there's 2 possibilities. If the radiation is bigger than the sample size, the radiation just travels through the material. It does not react with or interact with the material. Any energy transfer is controlled at the boundaries. If the radiation is smaller than a transparent sample, it interacts with the material. There's energy transfer, and it can be significant, and that's by absorption due to electronic or lattice excitation. So opaque refractory materials, there's no contribution to photon conductivity, and this is the 2 cases for a transparent material. Now, why are we concerned with photon conductivity and refractories? Well, that's because they're opaque materials, but they have porosity. So there can be radiation across pores. And that's important if you're designing an insulating material. You want to take into account radiation, because that becomes significant at high temperatures. So for porosity, in the case of porosity, if the mean free path is greater than the pore size, you have effective energy transfer controlled by the pore surfaces. And this is usually the case. The mean free path for radiation is much larger for photons than for phonons, on the order of centimeters and meters. So K effective is described by this equation. So this is the conductivity across the pore, 4 times, again, the Stefan-Boltzmann constant, times the refractive index, temperatures cubed again. Now the diameter of the pore is in the equation, and that's times 2 times the emissivity divided by times the emissivity divided by 2 minus the emissivity. And the emissivity is just a measure of how effective a body absorbs or radiates radiation relative to a black body. It goes from 0 to 1. So this effective radiation across the pore is proportional to temperature. So it goes up at high temperatures, but it's also proportional to the pore diameter. So bigger pores, higher thermal conductivity, smaller pores, lower thermal conductivity. Small pores decrease conductivity, large pores increase conductivity. So in the case of a refractory, when you make a press of refractory by a powder process technique, you're usually going to have 10 to 25% porosity after sintering. In a refractory that you're designing, like an insulating fire brick, you may have 50 to 80% porosity in the structure. And the same thing might be true for a fiber reinforced or fiber insulating material. So if you want to have a highly thermal insulating material, you want to put a lot of pores in because the conductivity of air is much smaller than the refractory material, and you want to have very small pores. So that's where photon conductivity becomes important in porous refractory materials. So here's a plot of basically thermal conductivity versus temperature for different refractories and ceramic materials. MgO is near the top, so is alumina. And if you look at the shape of these curves, we're starting at about room temperature and going up to high temperatures approaching 2500 C. You can see this drop in the conductivity. That's the 1/T drop. So as the temperature increases, the conductivity drops as a 1/T relationship, and it starts to level out. But in these cases, these are porous materials. So now you have a photon conductivity contribution at high temperatures, increasing the conductivity. So here we have photon conductivity in the 1/T relationship. It would still start to level off, but now the radiation across pores due to photons is taking place. So that explains the shape of these curves. So Al2O3 and MgO are very high. Graphite is extremely high. And down at the bottom, here's a mullite, a zircon, a quartz, which this one really increases because it's probably quite transparent. There's a lot of photon contribution and ZrO2. And vitreous silica obviously is transparent. It just does a lot of contribution from the photon conductivity. So for some typical refractories, these are insulating fire brick. This is thermal conductivity in English units. It's BTU times inch per foot squared times degrees F times hour. So conductivity versus temperature for some different types of insulating fire bricks, IFBs. They go from 2000 to 2300 to 2600 to 2800 to 3000. Those are the typical use temperatures for IFBs. They're made to these temperatures. And As you go up in temperature, you have to increase the alumina content. These are alumina silicate materials. So increasing the alumina content, you're adding a higher conductivity phase, you're increasing the bulk density, and you're decreasing the porosity. So the trend here, as you go to a higher temperature IFB, you're increasing the thermal conductivity. So that's a typical trend for insulating fire bricks. For fire clay refractories, a low alumina semi-silica, a high duty fire clay, and a couple super duty fire clays. So as you're going from a lower duty to a higher duty fire clay, you're increasing the alumina content, you're adding a higher conductivity phase. You're also decreasing the amorphous silicate matrix content. So you're decreasing the glass content. And I mentioned before that glasses have lower thermal conductivity because they're amorphous. So you're decreasing the amount of lower conductivity phase in terms of the glass content. In terms of the alumina content, you're increasing the higher conductivity phase. So as you go to higher grades of fire clay, you're increasing the thermal conductivity. There's various grades of refractories here. If we look at the high alumina materials, anything over 50% alumina, there's a 60%, a 70, an 85, and a 90. So again, as you're going up in alumina content, you're adding a higher conductivity phase, and you're also decreasing any silicate glass in the matrix, which is the lower conductivity phase. So as we go up in alumina content of alumina refractories, we're increasing the conductivity. If we compare a chrome versus a chrome magnesite refractory, here's a chrome magnesite, and above it is the chrome material. There's a reaction that takes place between the MgO and the Cr2O3. It makes this intergranular magnesiochromite phase, which is MgCr2O4. It's a spinel phase. It's a much lower thermal conductivity phase than either one of these materials. So the chrome magnesite will have a lower thermal conductivity than the chrome. So as we decrease the magnesite content in the chrome magnesite material, the thermal conductivity should go up. If we compare magnesite and alumina, I showed on one of the other slides that MgO is a much higher thermal conductivity material than Al2O3. So I'm just showing here that MgO is a higher conductivity material. If we look at MgO magnesite versus MgO or magnesite chrome, again, we have that same reaction between MgO and Cr2O3 that produces a magnesiochromite, the spinel phase, MgCr2O4, the low conductivity phase. So the magnesite chrome brick is less than the fired magnesite brick in terms of the thermal conductivity. So as we decrease the chrome content, the conductivity goes up. And then if we look at a composite refractory, the MgO carbon composite versus just the plain MgO refractory, carbon is a high conductivity phase. So when we add carbon, we really increase the thermal conductivity. So here's an MgO refractory. And then on a different scale here, here's the MgO carbon material. So by adding carbon, and these are usually 10 to 30%, this one's 20% carbon, we significantly increase the conductivity. And that's important for a lot of applications where you want to control corrosion by adding a non-wetting carbon as the matrix, and you want to increase the thermal conductivity to decrease the thermal shock. So MgO carbon is much higher than MgO. And another one here, the thermal conductivity of high alumina fire clay increases with increasing alumina content because it's a higher conductivity phase, and decreasing matrix content because it's a lower conductivity phase. These are all castables, basically alumina silica based castables, going from a vitreous silica, fire clay castables, super duty fire clay, and then the higher aluminas up to 90%. So even in a castable, as you increase the alumina content, you increase the thermal conductivity. Here's some more unfired refractories. These are plastics, and they're going up in alumina content from about 60 to 85, 90%. This one has a little chrome in it. So the thermal conductivity of these high alumina plastics, again, increases with alumina content because it's a much higher conductivity phase than the silica component. And you decrease the matrix content as you go to higher purity material. So you're eliminating the lower conductivity matrix phase. Where do you use thermal conductivity? Heat flow calculations. You want to calculate how much heat is flowing through a furnace wall. You want to calculate your hot and cold phase temperatures. So if you have a composite wall of multiple types of refractories, you can calculate the heat flow across the multiple types of refractories and the temperatures at the hot and cold phase plus all the interfaces in between. And thermal conductivity is also important for thermal shock calculations and design of thermal shock resistant materials. For thermal shock resistant materials, you want a high thermal conductivity. The higher the conductivity, the more shallow is the thermal gradient. The lower the thermal gradient, the lower the thermal stresses. So for thermal shock resistant materials, you want a high thermal conductivity. For insulating materials, you want just the opposite, a low thermal conductivity. So there's two ways commonly used to measure thermal conductivity of refractories. One is a water calorimeter, and one is what's known as a hot wire. So I'll go over both of these. So for the water calorimeter, there's multiple standards. The primary standard is ASTM C201. Then there's different versions for different kinds of materials. C182 for an insulating fire brick, C201, C202 for a refractory brick, C417 for a monolithic or castable, and C767 for a carbon refractory. They're all basically using the same equipment, but the sample setup is slightly different for each type of material. So the water calorimeter measures thermal expansion of refractory materials up to 200 in the English units, BTU inch per hour, foot squared degrees F, or in watts per meter degree C, about 28 watts per meter. The water calorimeter operates under steady state conditions, so the heat flow is constant across the sample. It sets up a large thermal gradient. You have a furnace on one side of the sample and a water-cooled calorimeter on the other side of the sample. And the calculations give you a thermal conductivity at a mean temperature. So it's the average of the hot and cold phase over this large thermal gradient. The test is important because it allows you to select refractories for your exact conditions. You can control the heat loss, you can control the cold phase temperature, and you want to control the temperatures so you don't exceed the limitation of the refractories or the limitation of the shell that may be confining the refractories in whatever vessel you have. You can design multi-layer refractory constructions by knowing the conductivity of each material. And these are provided in data sheets, so they're suitable for specification acceptance. So what the sample looks like, it's actually 6 9-inch straight. So 6 bricks that are 9 inches long, 4.5 inches wide, 2.5 to 3 inches thick. And they're laid out over the water calorimeter. So here I'm outlining the 3 bricks that are full size that are sitting in the center of the calorimeter. And then the other 3 bricks are cut in half to form the edges. So they're about 2.25 inches wide, or 2.5 inches wide, depending on the thickness of the sample. So underneath the sample here is a water calorimeter. I'll describe that in a minute, but it does have a center water calorimeter. There's actually 4 calorimeters, but the center is 3 by 3 inches, and that's where the measurement takes place for the heat flow. There are thermocouple wires coming into the middle sample over the center calorimeter on the hot face and the cold face to measure the temperature gradient. So the cross section, the total cross section turns out to be 18 inches long, 13.5 inches wide, and the thickness just depends on the sample size. The minimum thickness in this test is 2 inches, and the maximum is 3 inches. So 3 9-inch bricks. The center one is the test brick. The 2 other full-size bricks are the guard bricks. And then you have the bricks that are cut in half are the edge guard bricks that prevent sideways heat flow. So looking at it from the side, you can see the water calorimeters, the measurement one, and 2 inner guards, and the outer guard. And the little circles are the channels where the water flows through. That would be an inlet, and there'd be an outlet on each one of these guards. Here's the test sample right in the middle, and these are the thermocouples on the cold face and the hot face. So we're simply measuring the heat flow with this calorimeter through the center brick. We know the thickness and we know the temperature gradient, so we can calculate the thermal conductivity. It's a pretty simple way of doing it. And this is a 9-inch straight brick that's the center calorimeter over the center calorimeter. So it's 9 inches by 4.5 by whatever the thickness is. You can sort of see that this one was after the test. You can sort of see small grooves, and we actually put 2 thermocouples in the hot face and 2 in the cold face. So the wires are coming in under the cement, and they're crossing, and the bead is somewhere hidden, probably right about there. So there's thermocouples embedded in the hot and cold face. The heating chamber usually is capable of going to 2,800 degrees F. So you can put a temperature on the hot face of about 2,800 degrees F. There's a silicon carbide plate that you put over the hot face to provide a more uniform temperature, a more uniform heat flow. The copper calorimeter I sort of described a few minutes ago. It measures the quantity of heat flowing through the sample. There's a water circulating system that keeps the water at a constant pressure and temperature. So there's some type of chiller system that holds the temperature constant. I showed how the thermocouples are embedded in the sample. They're embedded in both the hot and cold face. And in the wells where the water comes in and exits on each one of the calorimeters are embedded differential thermocouples. So it's just a thermocouple that can measure small changes in temperature. So you're measuring the temperature of the inlet and the outlet water on each one of the calorimeters. So in the center calorimeter where you're making your heat flow measurement, the temperature rise of the water is what you're interested in because that's the amount of heat that's being absorbed by the water. So temperature difference between the center calorimeter, inner guard, and outer guards, what you do is you minimize the difference between these 4 calorimeters. You have the water flows balanced so that you have a uniform heat flow across the whole section, which is 18 by 13.5 inches. So you use the inner guard, the outer guard, and the outermost guard to balance the heat flow to make it uniform, and then you make your measurement on the center calorimeter. So the whole arrangement cross section looks something like this. So you have your furnace that's basically surrounding the sample on the sides and the top. You have heating elements over the sample. Here's your sample sitting down here, your 3 larger bricks, and then your 2 half bricks for the guards. The test specimen is right in the middle. Under the sample is the water calorimeter, and the center calorimeter is where you make your measurement. You have an inner guard on each side, and then the outer guard surrounds everything. You have a thermocouple to measure and maintain the temperature in the furnace at a constant temperature because it's steady state. And this is the silicon carbide plate I mentioned. The heat flows through the silicon carbide plate just to give a more uniform heat flow across the sample. The copper calorimeters look something like this. So this would be the 18-inch direction, the 13.5-inch direction. Here's your 3 by 3-inch center calorimeter. And then there's an entrance and an exit for the water through these wells here. There's a right outer guard, a left outer guard, and then a guard that goes around the entire calorimeter. So you have thermopiles and all these water wells, and you manually balance the flow of the water through each calorimeter until there's no temperature difference. And then you have uniform heat flow, constant temperature, so it's steady state, constant temperature, constant heat flow. So the temperatures between the center calorimeter and the guard calorimeters are balanced. The temperature of the hot face is constant. It's also constant on the cold face. The temperature gradient is constant. And then the temperature of the water that exits the center calorimeter is also constant. So complete steady state conditions. And you're measuring the temperature gradient with the thermocouples that are embedded in the test brick in the hot and cold phase. You measure the rate of heat flow through the test brick as follows. In a certain time period, and we usually use about 3 minutes, you measure how much water flows through the center calorimeter in a certain time period. Like I just mentioned, we use about 3 minutes in our lab, and then we measure the mass of water. And we know the temperature rise of the water flowing through the calorimeter from our thermopiles embedded in the entrance and exit water wells. So to get the rate of heat flow, and that's Q in BTUs per hour, we take the heat capacity of water, BTUs per pound degrees F. That's the specific heat capacity, times the temperature difference, which is the temperature rise across the center calorimeter, delta T, the mass of the water that flowed through the calorimeter in whatever time we specified, times T the time. So the rate of heat flow equals the heat capacity times the temperature difference times the mass of the water divided by the time. So we know the value Q, the heat flow. We can calculate K, the thermal conductivity. We know the distance between the hot and cold phase thermocouples. That's L. We know the area of the center calorimeter. That's 3 inches times 3 inches, 9 square inches. And we know the temperature differences between the hot and cold phase. So T2 would be the hot phase, T1 would be the cold phase. So a real simple calculation, we get the thermal conductivity at steady state conditions at whatever temperature we set the system at. A typical report would look like this. Here's the thickness of the sample. It was about 2.5 inches. Bulk density, 406 pounds per cubic foot. This is probably a very dense fuse cast alumina type refractory, very high density. When we have a high conductivity material like this, you can put a backup insulation between the cold face of the sample and the water calorimeter to keep the temperature of the water calorimeter low, because it is made out of copper and you don't want to have the cold face at a higher temperature than the copper melts at, or else you have a big puddle under the machine. So these are the different mean temperatures. So you have a hot phase and a cold phase. And you can see it's high conductivity because the hot phase is 390 and the cold phase is 383, only 7 degrees difference. So it's not very insulating at all. So you measure, you set it at different hot phase temperatures, you measure the corresponding cold phase temperature, the average is the mean. This is degrees F, this is degrees C. And then with the equation I showed, you calculate the thermal conductivities. And we do it in the English units and the metric units. So these are pretty high conductivities. Insulating fire brick would be less than 1. So these are very high conductivity for that material. And if you plot it, conductivity versus mean temperature, you get a plot that looks something like this. So as a dense refractory material, you expect it to decrease in a 1/T relationship as you increase the temperature. And that's in watts, and this is in BTUs, just the different units. And we fit the data points to a regression analysis so you can calculate the conductivity at different temperatures. The last method for today is thermal conductivity by hot wire. It's ASTM-C 1113. It can measure the thermal conductivity up to about 100 BTU, inch per hour, foot squared degrees F, or in the metric units, 15 watts per meter degrees C. So it doesn't have the whole range that the water calorimeter does. And if you remember, the water calorimeter is a mean measurement, mean temperature measurement. So it's measuring the thermal conductivity of a material in a steep thermal gradient. You have a thickness of 2 or 3 inches. You have a furnace on one side, a water calorimeter on the other side. So you have a steep thermal gradient. So you have a mean thermal conductivity. And the water calorimeter is not isothermal, it's steady state, but the thermal conductivity by hot wire is isothermal. The entire sample is at the same temperature. So you get different answers depending on what technique you use. The water calorimeter, because it's a mean temperature measurement, is going to give you a lower answer than the isothermal hot wire method. So if you're a refractory company and you're making an insulating fire brick, you want to use the water calorimeter for your data sheets. And that's what people do. So non-carbonaceous and non-electrically conductive refractories. So you can't measure an electrically conductive material by hot wire because you're putting a platinum wire in the material and running a current through it. So it would short circuit. So carbon, silicon carbide, silicon nitride are all electrically conductive, especially at high temperatures. And they also react with the platinum wire above 800 degrees C. They form silicides platinum silicides. They diffuse into the platinum, embrittle it, carbon diffuses in and embrittles it, so it destroys the wire. We've developed some techniques where we can coat the platinum wire with a boron nitride, a thin coating, and protect it from reacting with the platinum and make it electrically insulative. So we can extend this temperature quite a bit with the boron nitride coating. You can measure solid materials. You can measure the conductivity of powdered materials, granular materials, fibrous materials. It's pretty versatile. So the technique is simple. You apply a constant electric current to a platinum wire that's embedded between two bricks or embedded in a refractory container of a powder. The rate at which the wire heats is dependent on how fast heat flows away from the wire into a constant temperature mass of bricks. So it's isothermal. The bricks or powder, whatever you're measuring, is at a constant temperature. So the faster heat flows away from the wire, the more conductive the material is. The rate of temperature increase of the platinum wire is accurately determined by measuring its increase in resistance. And that's how a thermocouple works. The resistance is proportional to the temperature. Thermal conductivity is calculated based on the rate of temperature increase of the wire and the power input. So we measure the rate of temperature increase of the wire as a function of time, and we can calculate the power input. So this technique is useful to estimate heat flow, interface temperatures in a multi-refractory lining, and you can calculate cold phase temperatures of single or multi-component linings. And you can use the thermal conductivity values over a wide temperature range. And you can use the thermal conductivity values to rank or rate different kinds of products. The thermal conductivity values are at temperature measurements that rather than mean temperature measurements. So it's isothermal. It's not averaged over a large thermal gradient like in the water-cooled calorimeter. Because it's a wire embedded in a refractory, it's a radial measurement. So it's a combination of in-plane and out-of-plane conductivity. So if the material is isotropic, it doesn't matter, it's radial. But if you're measuring a material, maybe a fiberboard that's not isotropic, you have to be careful with this kind of measurement. Water calorimeters measure conductivity only in one direction through the thickness of the sample. So this is what a hot wire sample would look like. This is a full-size 9-inch straight, so it's 9 inches by 4.5 by 2.5. And you put this on a surface grinder and grind in a ledge. First of all, you grind the whole surface flat, then you grind in a ledge. And this ledge is on the order of 20 thousandths of an inch. Then you cut some grooves in for the lead wires. So here's what your platinum hot wire looks like. This wire lays right in the edge of this step, and then the 2 voltage leads come out through these 2 slots. You grind a second brick exactly like this brick, but with no voltage leads. And you take the brick and put it on top and slide it together. So this location here, you end up with something that looks like this. Your bottom brick, your top brick with the steps ground in it, you slide them together and compress the wire in that space. So the wire is now embedded in between 2 bricks. Of course, if you're using a powder, you have the wire suspended in the powder in a refractory container of some type. Here's an insulating fire brick, 9 inches long, 4.5 inches wide. You can see the step ground into the sample, and you can barely see the 2 leads, the voltage leads, and there's a small depression here for the thermocouple or the beads where the platinum wires are welded together. You need a furnace. When we go to about 3,000 degrees F, you have to be able to maintain a constant temperature plus or minus a degree F. And it's done in an oxidizing atmosphere. You need a power supply capable of a constant current in the 0 to 10 amp range and a stable constant current. We put a standard resistor in the circuit to get an accurate current from the voltage drop across the resistor, so we get an accurate current flowing through the sample. You need digital multimeters to measure the current and the voltage. There's a computer system that operates the power supply and controls the furnace and the multimeters for data acquisition. And the harness is platinum. You can use wires between 13 thousandths and 20 thousandths of an inch in diameter. We tend to use the 20 thousandths. So a schematic diagram of the equipment. Here's your furnace. Here's your sample sitting in the furnace. The wires embedded in the sample. There's a DC power supply that powers the system. The gauge length of the wire between the two voltage leads is L. You measure the resistance of that wire. You measure the voltage drop across the hot wire. Your standard resistor, you measure the voltage drop across there to calculate the current flowing through the system. And you use the digital multimeters to measure the voltage and the current. And there's a computer system operating on LabVIEW that controls everything. These pieces of equipment are, you build them yourself. I mean, Orton sells the equipment, but they're basically you build them yourself. You program the furnace to the desired test temperature. You power the platinum wire embedded in the sample at a constant current. And you keep the temperature rise in the platinum wire lower than 0.5 degrees C per minute. You're usually running a run between 5 and 20 minutes. You record the resistance temperature versus time data, and the time required to re-equilibrate between measurements is about 1 hour. You're actually heating the wire up pretty hot in that short time, creating a temperature gradient in the sample. So we usually run 4 measurements and we've got to allow an hour between measurements to get an isothermal condition again. So we usually run 4 measurements for an average, and you let the sample re-equilibrate over at least an hour between measurements. So it takes about a day to run up to temperature, get it isothermal, and another 4 hours to make the measurement. So it's about 1 day per temperature point. So if you plot temperature or the resistance of the platinum wire, same thing basically, versus the log of time, you should get a theoretical curve that looks like this, a straight line, a linear relationship. So as the time increases, the temperature increases, but the actual run looks more like this. I showed you a round wire embedded in a square hole. So there's, at the beginning, there's some non-linear behavior because of the wire sample contact resistance. At the end, there's heat loss at the outer surface. The thermal wave actually hits the outer surface and propagates backwards into the sample, and it becomes nonlinear. So you have a time between T1 and T2 and temperature T1 and T2 where you have this linear behavior where you need to measure the slope of this curve. So K, the thermal conductivity for a line source at a constant power input, the conductivity in watts per meter degree C is this K value here. that equals Q, the power input per unit length of wire, dL and T is time, divided by 4 pi dt, T is temperature. So you make a measurement as shown on this previous graph. You get T1, time 1, temperature 1, time 2, and temperature 2. And you use this equation. Here's temperature 1 and 2. I mean, time 1 and 2 and temperature 1 and 2. So now you have to get some other data, you have to get Q. So how you get that is you have to calibrate the platinum wire. You have to know its resistance as a function of temperature. You can use data that's available, but when you weld platinum wire and you bend it, you create dislocations and the resistance changes slightly. So you want to measure it. So dR dt is the change in the resistance as a function of temperature. It's the first derivative, so this is B plus 2 times C times T. So R is the platinum wire resistance at any temperature. A, B, and C are the coefficients of a fit to get this value R. So B is the slope of the linear region in the R versus L and T plot. And that just equals dR, dL, and T. We have dR dt over here. So we can put that in the equation and end up with this equation. The slope equals dt, the temperature change plus the constant B plus 2 times the constant C plus the temperature, and dL and T. So putting that in the equation, in this equation, you end up with K equals Q times B plus 2CT divided by 4 pi B. To get some of these other variables, I equals the current flowing in the wire. Vs is the voltage drop across the standard resistor, and Rs is the resistance of the standard resistor. So now we have the current flowing through the hot wire. R equals V over I. The resistance in the hot wire is given by V over I. We know I, we measure the voltage drop across the hot wire. Now we can substitute in for Q. Q simply equals I squared R divided by L, or VSV divided by RSL. L is I mentioned, is the length of the hot wire between the voltage leads. And substituting everything in, we have an equation for K. We can measure the voltage across the standard resistor, across our platinum wire and our sample. We calculated the constants B and C. We know the temperature. We know the gauge length of the hot wire. We know what the standard resistor is. And B is the slope of our resistance log of time plot. So when you make all those measurements and calculate, you get the conductivity at a constant temperature. And this is a typical report where there are 4 temperatures, 4 measurements at each temperature. So these are measured at about room temperature, 18 degrees C, and 262 degrees C, 647, and 979. And reported is the temperature, the resistance in ohms of the platinum wire before the test, and then during the test, all of these values that I just went over, the various voltages and resistances, are all calculated. This is the temperature rise below 0.5 degrees C a minute, and these are the calculations of the thermal conductivity in either BTUs or watts. So that sample has a bulk density of 37. The linear range was 9 seconds to 6 minutes on that resistance time plot. The wire length was almost 6 inches. So a low density material like this is an insulating firebrick of some type. So typically, a dense refractory shows a decrease in thermal conductivity as a function of temperature because of the phonon interactions limiting the mean free path. But an insulating fire brick shows an increase in thermal conductivity as a function of temperature because of the photon or radiation conduction portion across the pores. So this is typical of an insulating material, whether it's a fiber blanket or an insulating fire brick. Conductivity increases with temperature because of the radiation effect. This is another example at some different temperatures, from room temperature to about 1200 degrees C. And this is a much denser material, 180 pounds per cubic foot. It sounds like a high alumina refractory. 10 seconds to 6 minutes was where the data was collected, and the wire length was about 6 inches. So on conductivity versus temperature for a dense material, 180 pounds per cubic foot, you see this decrease in thermal conductivity, and then it gradually, if we kept measuring it, would tend to level out. I think that's the last slide on thermal conductivity. Are there any questions on this? So we did thermal expansion, heat capacity, thermal conductivity. Tomorrow, we'll do mechanical properties, which are elasticity, brittle fracture, and deformation or creep. And Wednesday, we'll do thermal shock and corrosion. And then we'll switch for the last 5 days to each type of refractory material, and finally end up with how to design a microstructure and how to design a lining. So if there's no questions, again, you can also email me or call me anytime. We'll stop for today. And I want to thank you for your attendance today, and I'll see you tomorrow. Thank you.